Thank you very much. Thanks for the invitation. And thank you again, Edward, for the nice intro. I promise I'll somewhere during my talk I will show a plot just like the one you drew here, but in PowerPoint and nice colors and with real data. So again, when I was invited to give the talk here, I was absolutely impressed by the poster. And I was thinking, how can I actually go and talk to these people? I'm going to talk about very mainstream things, and I pictured if I were to choose a similar picture for my talk, it would be something like this. Still weird, but not nearly as scary. And no CMB, but I will put a supernova here. So I'll be staring through the crystal ball of not only supernovae, but mainly supernovae because I'm very attached emotionally to supernovae. And I promise that towards the end of my talk, something will appear in this crystal ball. So stay tuned for that. All right, so. I'm almost embarrassed to show this, but 20 years ago, we actually made a Hubble diagram which had a single point. And I looked at this, and actually we were surprised when we had this Hubble diagram and we couldn't figure it out. So we said, well, maybe we need more points. Yes, we needed more points. So we went ahead, and this is the competing team. This is the Heisey team. They got a Nobel Prize for this lousy plot, okay? It's kind of amazing that it has so little data in it. I'm saying that not because ours was any better. Actually, it's about equally lousy in terms of data points. But it's actually kind of amazing how so few data points change, the way we look at things like gravity, like things like you guys have been talking about now. So, but still, time passes, and what I really want to talk about is where things stand today, and based on that, where I think where the field is going and what kind of precisions we are achieving here. So this is I would say the presently most complete compilation of type 1a supernova data. Does not mean that we don't have much more data on this. These are 780 supernovae. They are sitting probably twice that amount in people's hard drives, which what we put in here. But this is what's been analyzed in a very homogeneous way. And the answer looks exactly as in the first plot I showed you. I mean, the cosmology, really, the parameters haven't changed, but the precision has become much more robust. So what are you looking at here? Well, different surveys. This is the 3-year SDSS, Sloan Sky Digitized Survey of Supernovae. This is, again, 3 years' worth of data taking with the Canadian, French, Hawaiian legacy survey. A bunch of data taking at lower redshifts, and then this very limited data set at high redshift from the Hubble Space Telescope. Let me try to talk a little bit more about that, because clearly you can see that's an area where you could imagine that progress could be made. All right, why are there so few data points there? For you to understand that, I need to. This barely fits into it. Okay, I need to explain to you a little bit about Type 1a supernovae. What you see here is sort of a spectrum, what a Type 1a supernova spectrum looks like. And what you can see is that most of the flux is at optical wavelengths, with some limited flux at UV and the near infrared. Now, in the near infrared, first it's very hard to work. Actually, I'm an observer, so in near infrared, it's very hard to work on because for two things. The atmosphere glows very strongly, so you have to look at your source, which is behind an atmosphere which is very bright. But also the atmosphere cuts off. You can only observe through windows. There are some regions where the atmosphere completely blocks or nearly completely blocks light. So what happens then when your supernova are being redshifted due to cosmological redshift? Well, so what happens is that you see the redshift up here, and you see how the purple light, which is the one we usually measure, moves towards the infrared. Well, first of all, what happens is that the only thing that's expressed in the optical, which is what we typically measure from the ground, is this very, very limited UV flux, which is also very heavily affected by extinction, as I will be describing. And most of the action moves to the near infrared. Now, I told you that is accessible with the Hubble Space Telescope. However, what you have to remember is that the Hubble Space Telescope has a very, very small field of view, about 100 times smaller than what we can do from the optical from the ground. Therefore, it follows that it's very hard to find large numbers and study large numbers of supernova high redshift. This is something that will change when satellites will come online, like satellites like WFIRST, maybe Euclid, if they decide to do something about supernovae, and of course the next generation space telescope. But then let me go back to the data set we had, and I promised numbers, and so let me then show you a little bit how the data works in terms of constructing models and model parameters. So what you see here is, again, this Hubble diagram. I sort of keep changing between linear and log scale depending what I want to show. So I now move to log scale here. And again, the colors represent the different data sets, the low redshift, the intermediate redshift, and so on and so forth. So up here, in order to make it easier though, let me do it just that. First of all, this is called, toward my talk, this will be called the JLA data set. It's called Joint Light Curve Analysis, just because it used all these data sets. And the first author, I will refer to either JLA or the Tolerable data set. And this was published before the most recent Planck release. I'll be coming back to the most recent Planck release, but for the purpose of showing these plots, this is using the Planck data set as it looked for 2013, not that it will look much different than like this one. And also, as Edward explained, you can measure the expansion also, you can measure the background expansion also through BAO, and this particular data set, the contours you see up here are using 3 redshifts where this was measured by these authors. So then, let me then switch off the references, let me then bin the data, so it's easier to see. And what you can see here is that it's pretty clear that we have a very good handle on that. There is a need for something like lambda. Okay, it's a very clear need for something like Hubble Constant. And there's another thing you should see here is that based on this graph, you could say, why is this guy talking about supernovae? I mean, it's like the supernovae have these contour regions shown here. CMB looks wonderfully much more narrow, and if you combine CMB and the Byron-Cusick oscillation, that's what you get. So for determining that the accuracy of dark energy, at this point, the combination of CMB and Byron-Cusick oscillations is what really gives you the best constraint. However, we are all beyond this. We all know that there is something like lambda, so we want to measure, the next thing we want to measure is how similar to lambda is it? And ideally, we'd like to measure something which shows us it is not lambda. So then we move to the next plot. And what you see here is that it becomes increasingly more challenging. So the equation of state parameter, here the constant, here they make the assumption that it's still constant equation of state parameter. You see how it changes here, where -1 is lambda, and you see how different values, different from -1, would make your Hubble diagram change. And you see that it's pretty subtle. You can see that this is really starting to look very difficult. And not only that, it's becoming difficult also for other probes. What you see now here is, again, the supernova banana, sort of what is it like, the 68 and 95% confidence regions from supernovae. The green curve is the Planck data. And what the crossing here is that supernovae and Planck is the dark gray regions, let's see, right, and the red thing here is if you take Planck and BAO. So you see here, now things are becoming very, very comparable. The probes, you really need at least 2 probes in order to, if you were to claim an offset from -1, certainly I think no one in this room will be very convinced if it was only pointed out as one of the techniques. And the situation becomes, increasingly more challenging as you keep adding parameters. The next thing that people do is to look at this 2 parameter description of, and again, sort of completely phenomenological, not based on anything deep in particular. It's essentially the Taylor expansion of the equation of state, and what you see is that this is really, really, really hard, and you start to see differences which are, you almost see no difference at all, although this number is changing quite a bit. And here again, you see that it's not only for supernovae, but the even bigger contours here are if you use Planck with BAO. So there is not a miracle technique here. They're all having a hard time getting to the answer. And so the only, I think the take-home message here is that, there's not that you can just, get rid of one technique and just work on the other. You really have to have them all.
One question?
Yes.
These plots where you see this more variation with traveling, are you fixing the energy density to some...
Right, so here, to make it easier, I'm just varying one thing at a time. Yeah. Whereas, exactly, that's for the movies, yes. Right, so I promised to show a plot like the one Edward showed. I was desperately looking through my hard drive while he was talking, and here's actually the curve. I think he did a pretty good job drawing, actually. So this is the current data set, well, I think pretty much everything it says there. The one thing which is actually happening right now is that we have an approved program with HST, which is targeting the places in the sky which is a little bit easier to find high-redshift supernovae. So we're pointing the HST not at random spots in the sky, but at clusters of galaxies which have redshift between 1.3 and 1.8. In which case, whenever we find something, we're pretty sure, well, it's not pretty sure, but we have certainly a lot more chances to find something at the right redshift range where we think we need more points. Okay, so this is data ongoing. There are several supernovae being found, but I don't have anything exciting to tell you yet, except that, this part of the graph would actually be clean, according to our expectation, the error bar should shrink significantly. This is, again, this is not individual supernovae, but we're beating supernovae in similar redshift ranges. And again, we're going to redshift. All right, so then Planck came a few months ago, and nothing has really changed. The lambda CDM is as healthy as ever. If you're looking for any faults in the beauty, I guess some people are looking at this region, and there might be good reasons to look there. I'm not going to say more than that. I too see that deficiency there in the model. But other than that, lambda CDM is looking really, really good. Again, sort of all this progress, of course, all the different techniques, people working hard to improve the data they have, and not only did Planck improve on the data set, also there were new DAO surveys that had data published by the time this paper was written, so of course the Planck collaboration could include them in their analysis, and you see here now there were about twice the number of BAO redshifts as we had in our paper just in the beginning of last year. And again, to complement what Edward was saying in the other blackboard, there is also data on the growth structure. So there is, and in both cases, lambda CDM seems to be, its data is compatible with lambda CDM. There's no surprise there, unfortunately, I should say. Moving on to the next observable, or in a way, sort of going back to what I was showing you before. This is the W0 WA plane, and so the contours haven't shifted much from what I showed you before. The interesting thing to note here, however, which the Planck collaboration has shown very nicely, is that there is yet another observable that comes into the picture, which is the Hubble Constant. Somebody was discussing here about CMB and what you measure and what not, and one of the things that you have to keep in mind is that the CMB measurements are degenerate with the H0. So there are parameter degeneracies in what you get out of the CMB data, which have to do with which values of the Hubble constant you can derive from your data, or you can actually include from external fields. So I don't know if you can see it from the back of the room, but essentially there's a tendency of these ellipses will move, in this direction. Whether in this case you would have a very low value of Hubble constant, let's say it's like 65, and over here you are at 71 or 2. So clearly, people have been working very hard at trying to see, can we actually nail the Hubble constant? Can we make the measurement sharper so we can actually, improve our constraints further? I'll be coming back to that in a second. Other techniques then, just to complete what the Planck 2015 showed us, there is one more technique which was mentioned by Edward, which is the weak lensing technique, which at the time of this publication was using the same telescope as the telescope in Hawaii, which was used to study supernovae, But part of the time, part of the time telescope we use and the camera were used to study supernovae. The other part of the time just staring at some fields and measure the shapes of galaxies as well as it could. And what you can see here is, let's see, so on the green stuff, you can see the data, same parameter parameter phase space. This is now the weak lensing data, which has, about 154 square degrees with a median redshift of 0.7, which really corresponds to 17 galaxies per square eye minute. That's how many objects they could use to measure the shapes and therefore, be able to tell what gravity is doing along the line of sight. Just for comparison, I included here a note that Euclid, when it flies, and it sort of delivers according to specifications, it should have about 100 times more, in the best of the worlds, 100 times more galaxies in total. So that's, we can really look forward to a significant improvement here. Here is what the next graph here, the big triangle here is the same thing, but then you force it also to include a constraint on Hubble Constant. So you see how that helps. Still, weak lensing and including the Hubble Constant is worse than you can do compared to supernovae and this BAO. So supernovae and BAOs are still very, very critical and will remain very critical for understanding dark energy. There's no more CMB data. We don't expect any dramatic improvement in the CMB data for this purpose in a while, whereas we expect a lot of improvement in the other probes. So that's where I think we have to put our faith. Just to give a sense for what we could hope, this is a sort of a compilation a review paper I was involved in writing a few years ago, and I think what you said there still is true, that this is sort of the contours more or less given the scale of today. Scale as it was a few years ago, but it hasn't changed by much. And here's where we hope to be in 5-10 years from now, when some of these stage 4 surveys, as they are called, this next generation of dark energy missions are out there. And so here's sort of, we've wishfully thinking moved it away from the lambda point to show that, here's where we would love the thing to land, But it sort of gives you an idea of how much the improvement in accuracy could be really significant. That's what we are striving to achieve.
Sorry, here you're talking about data, or also because
I'm talking about
the control you have in weak lensing is not the weak lensing. The predictions from even from simulations.
Yes.
I mean the error bars that this figure will have are going to be big.
Right. So this is the product of all of the techniques together.
Ah,
right. Sorry, I wasn't clear about it. Sorry. All right. So let me then take a step back, because some of you probably remember that, hey, there was a problem with the Hubble Constant, wasn't it? Remember? So there was a problem that the planet used to like a lower value, and still likes a lower value of the Hubble Constant. The people working on surface and combining with type 1a supernovae used to like a value which is a few sigma away. I know I wouldn't overdo it, but it was some tension here. And just to make it even more weird, W map was in the middle. So it's one of these things where it was unclear what was going on there. And I would argue it's still kind of unclear, but there were a number of papers trying to say, see whether could you explain a different local value of expansion rate compared to the global value. And sure enough, people found out that obviously there could be differences, but not really as big. I think the consensus between everyone looked at it is that it would be very, very hard to get anything that big. So then people went back, observers like me went back and look at the data, and then you find something. And so in this Betulidon paper, people found something based on a different data set. It has nothing to do with the H0 data set, but I will come back to that in a second. People found something very unexpected. That there is a subtle, though significant, difference in the brightness of type 1a supernovae. The same type 1a supernovae we used to measure the Hubble Constant as we used to measure the dark energy. There seem to be some subtle difference depending on the stellar mass of their host galaxies. In fact, that turns out to be significant, statistically significant. So there's a step here. And actually that step improved in making these Hubble diagrams look tighter than they used to before in the movies I showed in the beginning. Now, this is actually not understood. Let me put it right down. It's not understood. But then observers have never been stopped at not understanding things. People just go ahead and check, what does it mean for any other observable? So some other group looked at what it meant for, could it actually be connected to even another thing? And sure enough, if you look, you find. So people found that, well, you know what, there is actually this brightness difference seems to correlate whether your galaxy is actually an active galaxy forming stars or if it's sort of an old type that has essentially run out of steam. And then that raised the question, wait, then what does it mean for the Hubble constant then? Well, this is what it means for Hubble constant. So obviously when we do the Hubble diagrams, we have a mix. So some of these galaxies have a lot of star formation, some have less. So when you estimate the Hubble, you do the Hubble diagram, you have a combination of both. Whereas the Cepheid host galaxies, which are used for Hubble constant estimate, they just happen, there are a few, so you can go and look at the measurables that people use to measure whether they are star forming or not, and they all turn out to be star forming. So then that means that you're using the Cepheid, you were using the average brightness of type 1a supernovae applied to the Cepheid host, but those were actually 10% different. So when they, or 9% different. So when they calibrate, when actually that's taken into account, the Hubble constant measured locally has actually gone down to a number which is at least now within the sigma from the Planck data. So I don't know if that's good or bad news, but it seems to be all in the systematics as usual. So that doesn't seem to that you need any fancy explanation. It's just doing your calibration better. All right, so that was it. So let me then emphasize. I emphasize the need for going to high redshifts, and let me now take for a second the alternative view that you also need to take a good look at the supernova nearby, and this is actually, by the way, a good example of it. So another way to look at it is to ask yourself the question, how well and how many supernovae do we have in those Hubble diagrams? So it turns out that maybe completely contrary to any intuition anyone else would have had, that the error bars on the high redshift sample are actually a lot better. So this is like the distance error based on for the different samples. And the SNLS, this group has worked tremendously hard to understand everything in the data. So they are actually the champions of measuring this supernova distances. Of course, as you go to a higher and higher redshift, you cannot beat Poisson, right? The uncertainties due to measurement errors get worse, but when they do at their best, they are actually get surprising, they get amazing good distances. Sloan have the same trend, and actually they were not quite as good at measuring distances. And if people measure the supernova nearby, first of all, there is a rise here which has to do with peculiar motion, right? That's nothing we can do something about it, right? But you could argue that why can't we nearby, as this thing goes down, why can't we actually do better on the this thing saturates on a value which is kind of nice. So it turns out then that when you do these Hubble diagrams, not only are we soon going to be complete, because of volume of course, it's much easier to find lots of supernovae at high redshift. You are populating these Hubble diagrams with lots of supernovae, well measured at high redshift, but we're sort of being a little bit weak on the low redshift world. And it turns out when you're fitting all these parameters, there is degeneracies and you want to be good at all of them. So that's one of the many good reasons why there is people work in our group we're leading a type 1A effort on the intermediate Palomar transient factory. This is, by the way, as you said, a collaboration that is looking at transients for a variety of reasons. Type 1A supernova is probably the least popular among this group, but we are doing that part of it. And it's a dedicated survey. There is a telescope on the sky every cloudless night, essentially looking at the sky in a very large field of view and finding supernovae, which are then identified at some of these other places at Mount Palomar or at other places in the world or on the globe where we have access to telescope. So this is sort of the field of view. about 0.72 point square degrees. Just to make the slide nicer, we broke one of the chips so we could put the moon in there in between, so everyone could appreciate the size of this chip. But it's pretty massive view of the sky. And this is actually going to, so when we find, as I said, we find supernovae all over the place. What you see here, actually, this is the locations from the sky. This is the Milky Way, which is bothering us, of course. Here's the places on the sky where the winter in Palomar is so there's the winter part of the sky that you can see from the winter, and the weather at Palomar is particularly poor in the winter, so we tend to find many more supernovae in the summer. That's where we have different populations. But this gives you the idea that we are pretty much populating the sky as homogeneously as we possibly can, and ideally we will be able to study sort of the gravitational potentials in the local universe and see whether, where the blood flows are going to be. And actually the thing I want to emphasize here is like we do it like we do it in high redshift surveys. Since we study the sky all the time, we find this supernovae very, very early, which gives us a completely different handle in how well we can measure this. We can actually do as well in principle, as well as people have been doing for the high redshift problem. This is just a warm-up. We have 1,600 supernovae, not all of them as nicely measured, of course, but it's just a warm-up. We are in less than, let's see, less than 2 years from now. We will be significantly improving the instrument in the sense that it's the same telescope, but the camera we are going from 7 square degrees to, actually it's wrong, it's 47 square degrees. And not only that, but the readout, everything's better. The technology is better, so we not only do we have much bigger, footprint in the sky, we also read out. We are much more efficient in the sense that we don't lose time reading out an image, for 36 seconds over here, we're going 10 seconds. So this will allow us to scan the sky multiple times every night, and this will give us easily 10,000 type 1a supernovae to match the growing number from the high redshift world. So, without going into any details, it's not only the numbers that count. We already hinted that we're limited by systematics many times, and the systematics that maybe comes to mind when we talk about supernovae. Systematics are different for different techniques, but for supernovae is of course a worry that we are not always correcting as good as we could for the extinction along the line of sight, and who knows, maybe we could introduce a bias since, the dust in a redshift 1 galaxy may not be the same as redshift, 0.2 galaxy. We need to understand that. And the similar is true for the brightness of type 1a supernovae. We need, of course, to convince ourselves and you that these things are actually the same. We can calibrate them to be the same distance indicator regardless of redshift. And this is work that is going on using this very well measured data set from nearby universe where you have the luxury of being able to study every detail. These things are so close that if you just find them soon enough, you can actually trigger all kinds of observations, like UV observations, infrared observations, everything you want. For example, all right, so one of the things we want to understand, for example, is which of these 2 pictures is right, if any of them, by the way. We used to, if you heard me talk like this a few years ago, I would have said, oh yeah, we know what type of supernova. This is a white dwarf and it's accreting mass from a neighbor, and it goes there's a threshold effect, you have a Chandrasekhar mass, and then it goes boom. Now it's actually even more likely that many of the supernovae we see is actually a merger of white dwarfs. And I say that because when we find a supernova very nearby, we don't see this big fat star that should have been there before the explosion. So we have now a couple of examples where we don't see this. I should add to that, we just found one such thing where it is a type 1a supernova, and it's one that would have been rejected from the Hubble diagram because it's very bizarre. It's one of the supernovae that, based on the kind of quality cuts we normally do in our data, we say, that one is not putting in a Hubble diagram. That one actually looked like this one. We do see any surprises. So there are surprises here.
Sorry, this is a purely observational fact or something?
Purely observational fact, yes.
So it could be, theoretically, you didn't know which one was.
So you know what? The theory camp is interesting. They all used to like this one, and now they're all liking this one, just because the data is moving. So of course, no, theories are not worse in this field than in other field, right? People are moving. So now the theories. So now if you go to a supernova theory meeting, they will tell you 80% of those, 20% of those. That would be the, just you put your eggs in all the baskets. So the theory is actually not much ahead of the data. I'll put it like this.
Then because not exactly for this, but for gravity waves, they say that we're going to detect gravity waves from astrophysical objects. Next time we turn on the detectors.
Yeah. Oh yeah, but this is a different story actually. So
different
all
story.
right, but it's a good point. Though. Gravity waves. Okay, so what people hope to find is very similar to this.
Yeah.
But you're really talking about neutron stars and black holes. That's what they expect. And don't get me wrong. I think these people are right. I mean, those things would definitely give gravity waves. The only question is that they have, and the same problem that people here have, is what is the rate? How many such systems?
Number densities, right? How many of them they are?
Exactly. So now what happened on that field that you're bringing up is that the volume has increased by a factor of 1,000 within a year from now. So I think in September 2016, the upgraded LIGO opened up 1,000 times the volume, 10 times the radius, 1,000 times the volume. So I think now they have a real chance to find something. That will be really exciting. And we, of course, want to find the optical counterparts. I'm putting this, but I mean, I want to find the optical counterparts with our ZTF, survey. That's one of the reasons why this thing is actually being built. All right, so again, without going into any technicalities, one of the things we really need to understand, I mentioned that, is how we correct for extinction. This is a little bit like the sun going down the horizon. The more extinction, it changes the observed colors of our supernovae, and we have all kinds of empirical ways to measure that. And of course, what you should remember is that we have a good shot at measuring this in the nearby universe, because the one thing that extinction does is that it affects the UV in sort of the shortest wavelengths more than the longer wavelengths. And again, we have this Hubble Space Telescope up there. Whenever there is a very red supernova, we can go and ask for time, and hopefully we get it, and then we point it with the UV instrument, and then we can actually measure the extinction law and compare it with the models we use for in our Hubble diagrams. And actually, surprise, it was different. So I'm showing you a paper, a couple of papers in progress, one which is already published and one which is in progress. And of course, for every supernova we measure them very nicely. We do get slightly different extinction laws than from each other, which is not very surprising. But here's clearly some room for improvement. In our cosmology now we assume they're all the same. And we know that we need to add that sophistication, and that they are not all the same. And I think, all of these things, in my mind, will contribute to make our error bars smaller, because right now we are oversimplifying. We are doing the sort of spherical cow approach, and we know that that's not completely accurate. All right, so I hope I didn't bore you too much with, you're busy working on extended gravity here. I bore you with real measurements. I think my conclusion would be that, first of all, I really want to emphasize that no matter what people tell you, you need all the techniques. And, if someone wants to sell one technique and tell you the other one technique is useless, be skeptical about it, because I think you would not trust any ruling out any theory which is only based on one technique, because you already seen, right? All of these techniques have flaws. But having said that, there is some quite significant strength in the fact that lambda CDM really fits all the data very, very nicely. And so I guess among all those fields, of course disregarding CMB, which has been going, people have been working for ages, Type 1a supernovae is the most mature of these fields, and we are been working on this, some of us, for over 20 years, and we've learned a lot. And clearly, this progress, we are a bit ahead of the other technique just because of that. Although I think all the other techniques have equally good potential. As I mentioned, we are now have an ongoing program filling out the highest redshift, and that will of course be taken up by future satellites. I mentioned these ongoing efforts at the lower redshift, which I think on the long run will be very, very essential for, again, our credibility of what we understand. Each one of these supernovae, they are so close that we can, I want to emphasize it, we can get a spectrum, we can do measurements that we can never do at high redshift. We can find galaxies in the local universe that look just like galaxies at high redshift. So we can really learn. It's not like we learn about something that is not applicable. It is very applicable. It's just that the demographics change, but there are examples of galaxies also in the local universe. I mentioned about extinction. I did not have time to talk about it, but there is also a possibility that we are now using the standard camel approach at an optical wavelength. It could well be that in the future we may consider looking at the reference near infrared. That's something we are actively looking at. And there is a fury of activity in the astrophysics world trying to, I think, make the probes that we need for dark energy as reliable as possible. And here I am in my promised picture of the lady looking at it. All right, thank you.
Can you explain again this issue of A0 and the measurement?
Right, so, yeah, sorry, maybe it was too fast. Let me, are you familiar with the original problem? Just understand where I started.
Yeah,
You're familiar with it?
I want to understand the solution.
The solution. Well, the proposed solution, let's be cautious about it. There is an obvious problem, which is the host galaxies, just happens, there are 6 or 7. Of 6, 7 supernovae which have been used for their Cepheids. They're all like Virgo cluster or closer. There are more star forming than the average type 1a host galaxy, which is used for the, to tie the entire population of peak brightness. So you are assuming both are the same, but in this proposed solution, there is actually a difference in brightness by 10%. Once you do this correction, you select from the larger sample the host galaxies which should have the same brightness as the ones matching the Cepheid host galaxies. Then the Hubble constant goes down by about 3 sigmas from the original measurement. Yeah. Or no, that's 3 kilometers per second, sorry. 3 kilometers per second. Sorry. Per megaparsec, yeah, sorry. Getting tired.
Question?
Yeah, no.
Yeah,
I see 3 hands, I don't know.
Just how many supernovae are expected to be formed typically for in the next 10 years?
Right, so depends, so let's see, so the numbers are huge. So if I, for example, for this Zwicky thing, the local universe is 10,000. For the dark energy survey, which is ongoing, they probably will have 5,000. LSST will actually have, which is hundreds of thousands per year. But you have to be careful with the numbers, because not a discovery does not necessarily mean that will be a point with small error bar and Hubble lagger. I want to be cautious about this. So the statistics is going to be more than you can possibly handle. The bottleneck will be how many of those supernovae could you actually get the sufficient accuracy in your spectroscopic identification, or whatever means you want to use to convince yourself and your colleagues that this is a type 1a supernova, and then you understand extinction, for example. So those numbers will be significantly lower. But easily, we will easily, if you can, it will easily be 1 or 2 orders of magnitude larger than you see today, easily. That's not going to be a problem, I think.
Yeah, so then you can, use that also to study the growth rate. I guess, with the fluctuation of the luminosity distance due to lensing. So then you can depend on the intrinsic dispersion of the supernova luminosity, but in this case, you can spot the growth rate with the supernovae. Because the luminosity distance depends on what is inside between the supernovae and the observer. So.
Right. So you're talking about weak lensing of supernovae. Is that what you said?
Yeah.
Right. So what you have to remember, though, is that weak lensing is democratic. On average, it sort of averages out, unless you have a bias that wanted to find the ones which are lensed. So at the moment, weak lensing is a small effect that is not limiting us at the moment. Maybe at some point it could, but it's not really at the one of the frontiers we need to improve right now.
No, but just use the dispersion. If you use the dispersion, you can probe what is the variance. Of the if you measure the variance of the luminosity distance.
Yeah.
Well, then you can probe what is
I'm sorry, I misunderstood you. You want not to see as a problem, but as a virtue. Okay, you're saying use weak. Okay, sorry, I misunderstood. you're saying, yeah, use supernovae as weak lensing probes. Yes, absolutely. With LSST that might happen, yes. So you have to be at significant redshift. Yeah, sorry, I missed you. Jump to your question. Yeah.
Suppose W starts varying beyond 1 point, say equal to 1.5 or equal to 2.
Ouch.
Then you will see it.
Ouch. Right, because you see, remember how the things works, right? Supernovae, we proved expansion is integrated from the redshift where the thing is measured to the present. So if we measure something, let's say at endpoint redshift 1 or 5, obviously anything that happens there or much closer there, it's going to be, that's not going to be measured with supernovae, I think. However, well, I think that's going to be very poorly measured. BAO might be better there because there are already measurements of BAO going into redshift 2 with this Lyman off. They are very, I should say, the first numbers that came out of that were very weird. Nobody understands really what they measured, but that doesn't surprise me. It's the first time but people have been measured in the sort of the counterpart of the background part, expansion part. They don't measure the Luna distance, but they measure combination distances, so which you can convert to Luna distance, and which goes all the way to redshift 2. So I think that's, to me, that is extremely exciting. And again, it's just a matter of time before they get understand all the astrophysics. But I think we'll get in there. So I think, and that's something that will be addressed by future missions and even ground-based, lots of ground-based efforts. So that's going to be a number that's going to be improving a lot with this extension.
Also, you shouldn't forget, for example, things like 21 centimeters, like SKA and so on. They can go to really high redshift in principle.
Yeah, I hope so. I mean, I'm not sure what SKA actually will be. I certainly hope so. I'm a bit confused about what SKA will do or not. But in principle, of course, that would be the holy grail.
4-5 or something.
Sorry?
Yeah, claiming even going to 4-5 on redshift.
Yeah, I've seen claims and I've seen claims of the opposite. I don't know, but yeah.
So I have a comment. So you were stressing the beautiful successes of the landed CPM model. I think there's one area where there's growing tension. And this concerns supermassive black holes. We are discovering that supermassive black holes higher and higher redshift with larger and larger masses.
It's funny you mentioned that.
Just an advertisement that's going to be paid
I have another
on the archive.
2 hours ago, I was giving a talk about that. So some people are laughing in the audience because I was talking about exactly. It was another meeting. I was giving a talk. I completely agree. That's an exciting field where things are happening. However, again, I wouldn't. It's the astrophysics and the way people estimate the masses of those black holes. I think it needs some more thinking whether that's completely accurate or not. But I agree with you. In principle, it's a puzzle. It looks like a puzzle, and maybe there are experts in the audience here that can comment. But I'm not super convinced that we need to abandon lambda CDM because of that. But we might have to.
You might have mentioned this already, but talking about this black holes, can you measure the image distance to AGN? Can you get something from there because they go up to that level?
Right. So there's a case where you can do that. There is actually a group in Copenhagen that has proposed that, and there are other people. So again, all of these techniques are in their infancy. So I think the answer is yes, but they still have to understand the systematics, and this is very tedious to measure because it's not just going and measure the brightness you've done. You have to measure what they call this reverberation time mapping. You have to measure how features change with time. So it's not like your your brightness that you've done. It's complicated, and right now I would say it's promising, but nobody has ever suggested that it's among the top techniques at the moment, but that could easily change. But certainly some people are working hard.
That's not done yet.
It's not done. People are thinking about it very hard, but it's not done yet. Yes.
Okay, I think you have to stop here, unfortunately. So let's thank Ariel.